Okay, welcome back after the break. How's your break? Is it a good break or is it a breakdown? For us, it's a breakdown because we have so many work to catch up, creating your material, go through your markings and creating the quiz tomorrow, of course, and so on. Okay, so I hope you have a good break. We need some rest. Don't rush too much about sometimes you just need to give yourself some rest, okay? So today we'll continue on our course. So we'll get something slightly easier than the PST3. But before that, one very important thing, you know that tomorrow we are going to have a quiz, okay? So uh, am I sharing the screen? I may have the mistake of not sharing. Yeah, I didn't share the screen. Okay, so one very important thing is tomorrow we are going to have uh, a quiz that all the details are there. And I will say, even I post this, a lot of students will not read this. The first thing is very importantly, bring a pencil. Okay, it's like those multiple choice test paper. It's paper and pencil. You will need to bring a pencil to shade the option in which you may need to correct it yourself. So bring an eraser. I said it very repeatedly and redundantly because every year we still have students coming in, don't have a pencil, and then after they choose the wrong answer, they want to correct it, but they cannot. So sorry for that. It's computer marked. You are the one who is being responsible for your marking. Okay, you know all those public exams are like that. You have to be responsible. So please remember to bring a pencil. For the rest of the question, I allow you to use pencil. Okay, so you don't have to use pen. There are some written answers and this and that. You are allowed to use pencil, but please use some black pencil that is in deep color. Don't use those H. You know, pencil have two types, right? H and HB. H is those very light color. A normal pencil usually we say we use is HB, but I would suggest you use B or even 2B to 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 shade your answer and to write your answer. Because we are going to scan all your script into a system called SoftMark, and we'll mark from there. And then you can have all the electronic version of your marked paper and distribution very easily. Okay, so please remember to bring pencils. If you're kind enough, bring one more. Okay, in case your good friends didn't have one. Also, there's another very important thing is we have two venues. Because this room supposed not enough for people to sit with spacing. Now you are sitting comfortably with your friends, you can be together. But for our quiz, we need you to separate. So just in case somebody will look at the other's answer. So please observe that. Go to your own NUS registry or your name. So we have this class name list, right? If we go to depending on this, okay? I don't care whether you put your English name first or you Peter, Paul, and Mary or Alan or whatever it is, we use the first character of this, okay? Some people will, usually for Chinese, we put our surname first, right? For example, Tang Aping, okay, is T. Some people will put this English name first. So for example, John Tang Aping. I don't care how you arrange, but we'll use this one. Whatever your first character is, you go to the right venue, okay? So the venue distribution is also specified in this information. If your letters start with from A to L, please come back to this venue. If your first letter start with M and after, please go to LT16. Actually, LT16 is just beside. Okay, so even you got it wrong, it's okay. You can go back and forth immediately to the other venue. Okay, so we'll have two venue. One more thing is, please read through the rest of the information like the scope or cheat sheet. The one last thing is, as we stated at the beginning of our semester, we can give makeup midterm only on MCs and NS. And if you have another course, I don't know why we have another course clashing with the time being, please negotiate with me. Actually, there was one student trying to resolve that, but luckily we resolved that, okay? So, but if unfortunately, because of some reason, like MC, you cannot make it tomorrow, we already told you the next makeup midterm will be on the next Thursday, 10 a.m. Okay, so next Thursday after the Thursday lecture, we'll go to LT19 to have a makeup quiz for those people who cannot make it. But if you miss that, too bad. You miss all the quizzes already, okay? So this is one piece of very important information for everybody of you. The most important thing is please bring pencils. Okay, I know that it's not natural nowadays. To be honest, I haven't been used my hand to write something, even pen or pencil for a long time. Okay, so please prepare your pencil. And also this format will be the same for your quiz 2 and final. Your final will be the same. And if you talk about the real quiz question, please go to some past paper. Will be very similar. The first part for quiz 1 is time complexity, and there were some true and false, and there's some other question at the back side of the paper will be some sorting question and this and that. Okay, but keep in mind, this year we run the quiz 1 week after the BST, so they will include the topic of BST. In the past year, quiz 1 is before BST, so you will see the past year quiz 1 didn't contain BST. Balanced binary search tree. Okay, so please be careful about that. If any question, please ask it in the poll everywhere here. Okay, there's a poll everywhere. If you have any question, please ask, or you can go to our Canvas link to go to the link. So there's the quiz. Usually, don't worry too much about it. I think quiz 1, if you have been keep up with our lecture, getting a B shouldn't be a problem. Okay, that was my learning objective. If you come to my lecture, listen to every of my jokes or memes or whatever, then you should be able to get a B in the quiz. Okay, but of course, if you want to try for an A or A plus, that's another story. You need to spend extra effort. And again, this course is not bell curve. Okay, there's no bell curve. So if you are all doing well, I give you all A's. I will argue with my department why I give all A's. If you are all cannot make it, I will give you all F. Okay, but of course that won't happen now. Okay, I also trust my teaching. It won't happen, right? So so just want you to know that there's no bell curve. So the grade is quite already set. So yeah, usually quiz 1 and quiz 2 are quite good results. Okay, usually the average is at least 60 marks or something for quiz 1 and quiz 2, usually in the past. So relax, quiz 1 is easy. And also the other thing is usually every quiz part we have set the question is easy, medium, and hard. Does it make sense? For some time complexity, I have one easy one, one medium one, and one hard one, and so on. So to differentiate students. So what I want to tell you that is because don't be too unhappy if you cannot answer all the questions. And also don't be too happy if you can answer some question, okay? That is to differentiate student of easy, medium, and hard. Okay. So if any more questions, please ask it in the poll everywhere. And we'll start today. And let's see. Oh dear, error already. So I'm trying to run these tests. Let's reduce it a bit. Run again. Okay, so what are we going to do today? We are going to do hashing. Just a personal experience, okay? Before that, let's talk about history. In my uni time, I don't care about hashing. I don't know what it is. I thought because at my time, my algorithm teacher was very dry and boring. I remember at that time, you know what my algorithm teacher did? My algorithm teacher, at my days, we teach you transparency. Anyone know what is transparency? You don't know what transparency is not like this. In our old days, there's a projector, and the lecturer will write a note on a transparent sheet of plastic paper and put it on the projector and like PowerPoint. We don't have PowerPoint, okay? And one thing I remember very much is the lecturer is like pointing at the transparent sheet and then teaching the lecture, and somehow the transparent sheet fell on the ground, and he's still talking, and his finger is still moving. Yeah, so my teacher was very bad, and I don't like hashing, but that was a big mistake of me, because hashing later become one part of very important, popular, fast algorithm that always people use. Okay, and just before that, let me tell where is the hashing. If you are using C++, you have some data structure called hash map. If you're using Python, there's some data structure called dictionary or set. They are all hashing. Okay, you have been using it if you already are using Python or C++. So let's see what this is. So remember, we have this data structure for our BSD, which is a symbol table or dictionary. What we want you to do is, let's keep some record that have key and data. In a whole, actually, we're keeping all the data, but we want to organize the data by a handle. For example, if I want to search for your record, I want a handle, which means how do I know which record is you? Then that is the key. For example, I use your student number as a key. So if I search for your student number and I can retrieve all the other data. So it's a key and data, which is what we call key and value. For example, remember this example? The key is maybe the key can be any part of the data. I can use different key also for multiple key references. But let's say if we use the key for the arrival time or departure time, and then each departure time will be related to the whole data. The whole data includes what is the flight, where does it go to, what is the plane size, what is the plane model, which airline is it, and so on. So we use the key as the timing, and you want to retrieve the data. And airport example may not be a very good example, because in one day you may not have so many airplanes. Okay, maybe you have at most 100 or 200 airplanes, which is not a data set. But if you have a large data set, it will be very important. And we also emphasize that the world is not beautiful anymore, because we need to modify the data. If you already have a data set, you may add new one or delete the old one. Because without dynamic structure, because if you already have a static data that won't change, why do I need this? I just sort it, right? I just sort the data. And I sort the data, I can do whatever I want. Everything is in log n. Okay? So, but we need a data structure like our BSD tree that will add data and remove data. And we want to do queries. Is the data in my data set? What is the value and so on? But one thing good today is, let's don't talk about successor and predecessors. Okay, we just need to get data from our data set and also check its existence, add or drop. We reduce the functionality by not having the successor or predecessors. So we don't want that. Will that be better? Let's see. So this is our dictionary ADT last time, but today, because we don't want this, we only need the ADT that I can insert data into my data set, I can delete data in my data set, I can retrieve data in my data set, and so on. Okay, so it's a simpler ADT. And what is the use? A lot. For example, the real dictionary, the key is your English word. What does it mean by photosynthesis? Then that is the key, and you go to the dictionary and then retrieve the value. Phone book. I know right now you don't have phone book. Maybe internet DNS. What does that mean? You actually put a URL, www.nus.edu. Actually, you need to return an address. You need a translation or compiler compiler, each of the variable have a name, but then you have all its data. Where is its address, what, whatever. So you have all these key and data pair. For example, if I want to store that, I can just store in a linked list, right? I can store a linked list and then I search for it. Of course, you know that it will be super slow. If you have n data, your searching, insertion, deletion in a linked list can easily be log n. Sorry, not n, on. Okay, this is of course not good. I can put it in a sorted array. If I assume that your sorted array is sorted already, searching anything can be log n because I can use bisection method, the binary search. But the problem is, if I want to add new things or remove new things, I need to insert the item into the sorted array. That position, I need to shift everybody. Okay, so for example, here you're sitting comfortably. If I want to insert anyone here, you two have to shift. If the queue is longer, more people have to shift. The worst case is the whole class in the shift. Okay, so which is bad, which is on if you insertion. Of course, I can do something like unlinked, like a linked list. I don't care. I just put anything in a random set. Insertion will be O1. Okay, that will be easy because insertion is just dump everything in the heap. But then searching thing is you need to go for everything. And of course, last time before the break, we learned binary search tree. And binary search tree, if please take note, one small hint for tomorrow quiz. That's a difference between binary tree, binary search tree, and balanced binary search tree. Read carefully about the question, okay? If you just talk about binary search tree, the insertion deletion can be on. But only if it's a balanced binary search tree, then all the operation can be log n. Okay? Can we do O1? Can we do this wishful thinking? Wow, what is that? That means I don't care how large your data set is. Maybe it's a million, oh, just now we have the Singapore news, right? Singapore just exceeds 6 million people. And we can talk about large country like China with 1.4 billion. Indian, how many people? Is India more than China, or I don't know what is the population, or the world? What if your data set is really large? O1, what does that mean? I don't care how large your data set is. Every insertion, deletion is O1. Is that possible? Let's see, okay? For comparison of, so this is some of the other, if you use spelling correction, you are actually using this kind of data key and value searching, web servers, and usually why we mention it again is log n is not enough, not fast enough. N is super huge. Before that, let me show you some Python code. Sorry, in Python, because I just, they don't have a C compiler here. What do I do here? For those who don't know Python, I explain the code. I have a number here, and what I do is I generate an array. Anyway, this array I try to generate is some random number, okay? Some random number in the array, but the number of the item in the array is the number divided by 10. And some some call random number. So anyway, it's just a random number array, but the size is quite big. And in the same time, I create a dictionary, which is a hash table data structure in Python. Okay, what I do is very simple. I just search for some number called x. In Python, you can search for something in like this. So it's just searching if the number is in the array. I also search if the number is in my hash table or dictionary. Then I print out the time, okay? And let's see what is the result. If your array have this, how many items? 1 million. If your array have 10 million items, my search time in dictionary is 1 millisecond. but my search time for list will be 0.1 second. If I increase the size to 100 million, so this million, right? 100 million, then my search time will be, this is about 2 milliseconds, but then my search time for list is about 0.7 seconds. And then so on. This one, you can see the time difference is so big. Why? Because for list is the unsorted set, you have to go through the whole list to find your item. Of course, you put in a tree is better, but it's even better if you put in a hash table. Okay. So today we talk about why is it so fast? Why is it so good? Okay. And this is the dictionary structure in Python, which is equivalent to our hash map in C++. Let's continue our lecture. Yeah. So there's a few assumptions. First of all, we assume there's no duplicated key. What does that mean? That means I don't allow, for example, just now the airplane example, I don't allow two planes have the same arrival time. Makes sense, right? How can two planes landing in the same time? Well, maybe you have two runways, but let's assume there's only one runway. There's no two planes can land in the same time. But this is a bit maybe not comprehensible. No mutable key. I don't know anyone you remember if you learn Python or whatever, there's something called mutable. What is mutable? If you use an object like a key, you cannot modify that internally. Okay, what does that mean? Let's see this. For example, I want to put this. The time is the key. The plane is actually the data. What I do is time is equal to 9 o'clock. Time is equal to that. So I insert SQ001 is time 1. SQ002 is time 2. So time 1 is already set as the key of SQ001. But now here, I mutate the time. That means the time object inside my data structure has to be changed. And this is not allowed. That means your key inside your data structure is not allowed. For example, if you know that Python dictionary is like that. For example, I can create a dictionary in Python. Let's say dictionary 1 is equal to, the key is 1, and then your data is apple. The key is 2, and that is orange. Okay. So this one is a Python dictionary structure, which is a hash table. The left side of the colon is the key, the right side is the value. What I can do, I can add one more entry. I can say the key is 3 or 4, but then in Python, the value can be something mutable. For example, list. A list in Python is mutable. What does that mean by mutable? Let's say if my list 1 is equal to 1, 1, 3, 1, 2, okay? If my dictionary is equal to this and this one, okay? Okay, this is my dictionary, right? You can see that this value is a list, but I can mutate that by not going to the dictionary. I say list 1.n. So list 1 become like this, right? And then you can see the dictionary is got changed. You see that? The dictionary inside got changed. For a hash table, you are allowed to mutate. It's called mutation. You are allowed to mutate the value, but you are not allowed to mutate the key. So that's why in Python, you cannot add a key value. Let's say your key is actually a list. This is not allowed. In Python, you can say the error is unhashable. What is unhashable? Because your key is a mutating item. So it's unhashable. So that's why the key should be immutable. Okay, you can put a tuple as the key in Python. You cannot put a list as a key in Python. Okay, let's make some very simple hash table. Extremely simple. I use the table. Actually, hash table is a table. Let's have a very simple problem. What do you do after dinner every day in a week? How do you record it? Okay, I can simply model every weekdays by a number, right? Sunday is 0. Monday is 1, and so on. And what I want to emphasize is 0 to 7 is called a universal key set. What does that mean? This all the possible key you can have. You can only have Sunday to Saturday. You cannot have anything. You have Monday, you have Tuesday. You don't have Daniel day. You don't have a weekday. Okay, you only have Monday to Tuesday. That's all you have. So if you have a very universal key, you can simply put in the key and value. For example, you can put it into the data set. Sunday night, I would watch Netflix. Wednesday night, I will do exercise. Friday night, I need to go for a lecture. Okay, you can do that. It's very simple. So for this one thing about it, insertion deletion is very simple. I can quickly say, oh, Thursday, I want to add an activity. Thursday is my cleaning day. And then suddenly say, oh, my Friday lecture is canceled. I don't do lecture anymore. So deleting, inserting this is super fast, right? However, why is it fast? Because you only have 7 days. What if the time complexity for that is super fast because O1, because your data set is small? Now, all the keys are just the 7 days. What if you have more type of keys? For example, what do I do after dinner in the 7 days? How about I want to plan for the year? The year 2024. What do? I create an array of 365 slot, right? And each day represent 1 day of the days of me. But what if I want to plan my dinner after dinner for my following 80 years of my life? Then you need to create a very large array. And also the small problem is you may have a lot of empty slot. You're wasting your space. So one key point here is your whole space of the keys is very large. Let's say 80 years. But the problem is the slot you use is not filling in. You don't have things to do every night. So that is the gap we want to talk about. Okay, how do I do if I can live 8,000 years? How do I plan that? I need a table of 8,000 times 365. The table will be very, very large. Okay, because the problem is you're wasting memory also. Most of the night you do nothing. So the problem is that will actually spend too much space, because one thing about it, you are labeling the entry index by your key. So think about that. If let's say I want to create a table for all the students, and what I do is I base on their student number. Your student number is 8-digit or 7-digit. 8-digit, right? I use a number to put in the array. Then I need 10 million number because it's 8-digit. But on the other hand, if your key is all integers, too bad, you need to create a table of 4 billion entry, because there are 4 billion integers in what you can do. And what if your keys are not any integers? If your key is a string, or tuples or something else. But of course, one thing that what if your key is some floating one number? But the good thing is Pythagoras said everything can be converted in number. Okay, one thing is every data, no matter it's a string, is a picture, even if your iPhone pictures, you can all convert it into numbers. So we can assume all the keys are integers. Okay, everything you can actually transform it into a series of bits, and every bit can convert into number. So, for example, what is the longest English word? Actually, the longest English word, I don't know how many letters. I think it's 40 something letters. But let's assume all the English word has 26 letters, and each letter, because it's only 26 characters, right? Still 26 alphabets. So every letter can be represented by 5 bits. That means the longest word, actually it's not the longest word. You have even longer word. I can convert every English word into an integer. But the integer needs 140 bits. But the thing is, can I create a table that is 2 to the power 140 to store all my English words? And it's impossible because 2 to the power 140 is almost the number of atoms in the observable universe. Okay. And also the big thing is there's a lot of empty space. Okay. So that's not possible. And here we are illustrating the problem is there's a huge size of the key space. Just now, at the first example, we talk about a week. The key set is only 7 items, very small. But if you talk about other keys, for example, your student number, possible way is can be 10 million different keys. So let's say this set is all the possible keys. This possible key can be your student number or possible name, okay? You have to assume some people's name is A, okay? All possible name. We want to map this into a table, but actually you know that in the real world, we don't use all of them. There's actually no person in the world's name is A, right? And there's no person in the world is the surname is W. So even though W is a possible key in this universal set, we don't use all of them. The usable set is a very small set of words. For example, if the blue set is all the possible combination of the 26 English characters, that is less than 24 length, the universal set is very big. But you know that in our English dictionary, we have at most 1 million words. In our normal dictionary, it's like 10,000 words. This orange, or I don't call it, this peach color of usable key is very small. So we wanted to put it into a small table. Originally, the ideal thing is I put it into a table that is m to the power 140. And every English word directly translated into a numbers, then put it in the table. But then the problem is it's too much space. And it's not a good idea. And we cannot create that large table. So, for example, if I want to put all the English words in a table that it has a fast access, I need to create a table of 2 to the power 140. Actually, in real life, even if you want to exhaust all the human words, it is about 1 million English words. It's far less than 2 to the power 140 English words. Okay, so that means this is all possible combination of letters. This is usable English word. What I want you to do is, can we put this small set of words into a small size table? And this table size is M. This M is far less than 2 to the power 140. How do I put them? Okay, make it in a very another way. Let's say I want to put you guys into a hotel. Okay, vocation CS2040C to reward you guys. Hotel A, we go to Paris. So one smart thing we want to do is we want to put you into a room. We immediately know what your room is. What we do? We use your student number. What is your student number? Maybe your student number is 1, 2, 3, 4, 5, 6, 7, right? If your student number is 1, 2, 3, 4, 5, 6, 7, I put you in the room 1, 2, 3, 4, 5, 6, 7. How large is the hotel? The hotel need to have 10 million room, right? But if I only get CS 40, 20, 40 C people to that hotel room, do I need the universal set of 10 million room? I only have 200 students. You guys will be living in the hotel. Wow, very shook. Like surrounding 100 rooms and no people. Okay. But the trouble is, you may need to find other people in far away. Okay. So the hotel in the M bucket do not need to be 10 millions and do not need to be 200 and 2 to the power 140. You can have a small size. But then the question is, what is the rule I put you into the hotel room? Let's say I have a hotel size of 1,000. What is the rules that I use your student number to put in the hotel room such that I immediately know from your student number which hotel room I put into? Okay, that was an easy thing. Maybe I just use your last 3 digits of your numbers. Is it okay? The hotel is only 1,000 room. I use the last 3 digits of your numbers. Your last 3 digits. Let's say your student number is 1, 2, 3, 4, 5, 6, 7. I just use 5, 6, 7. I put you in the room 5, 6, 7. Is it okay? But of course, they will cause problem. Let's talk about the problem later. So the first thing is we don't need a hotel of what 10 million to store you. I want a smaller hotel. How? What is the rule? What is the rules that are based on your key to put you into the position in the array that I can recognize easily? We use something called hash function. Hash function is a function to convert your all possible key into a position in the list. That is the position. For example, just now the example. If my hotel have 1,000, I have a function. If your student number is 1, 2, 3, 4, 5, 6, 7, I will take 1, 2, 3, 4, 5, 6, 7, put into my hash function. I don't know what is it yet, okay? The hash function will produce a number. The number is directly one of the hotel rooms. That's the method. So all of these hash table things we build on one thing called the hash function. So that means the hash function will take the universal key and compute the hash function of the key and put it into the table. Okay. So there's a hash function. Whatever the key is, I'll put it on the table. So whenever you ask, oh, is the student number with 1, 2, 3, 4, 5, 6, 7 in the hotel? You can directly use the 1, 2, 3, 4, 5, 6, 7, compute the hash values, and then look for it in the hotel. Okay. Oops, sorry. The computing time is just the hash value function and the access the bucket. And assume the function call O1 time, your access put it in the table and is O1. Let's make a very simple example. Okay. Let's say the key is an English word, which is your food. And the value is the place of the food. Okay. And how do I create a hash function? Let's create a very simple one first. This simple one is the hash function. When I take in a key, is only the length of its character. This is not a hash function, okay? But just let's say that. Then how do I do this? So the hash function of pizza is 5. The hash function of coffee is 6. And that's why I will put the pizza Clementi in slot 5. I will put the coffee, it's not coffee, it should be coffee NUS, okay, not orange NUS. So you put a coffee NUS in slot 6. And now, without knowing it, I ask you, where is the pizza? You don't know the hash table, right? Then I use the pizza into the hash function, and we know that, oh, it is 5. Then I go to the table to find the slot 5. Oh, slot 5 is pizza Clementi. So that's why we have that there. Okay, now I ask you, where do I get cake? C-A-K-E, cake. Then I put cake into my hash function, and the hash function will return what? 4, right? Then I go to the table and see the slot 4. Do I have anything in 4? No. That means I don't have cake in my table. Okay? So this is how we use the hash function to access the table. Do you have let's say Goreng or whatever, let's say lemma, then you use the same thing. Let's say lemma how many letters? 11 or whatever. Then you use 11 to put it in the hash function and look for the table entry. Is it there? And insertion, whatever, is like that. What's the problem? What could be the problem? Yes? What could be the problem? Yes. What if I want to put another same number of letters? For example, I insert this and insert this. How about if 2 hash keys have the same value? Okay, it's clash. For example, what if in this example now I want to insert what? Insert bread, B-R-E-A-D, whatever, bread talk, whatever, 4 leaves. Okay, this in where? In Buena Vista. Okay, bread is in Buena Vista. Then where do I insert? It's supposed to insert in slot 5, right? Because bread is B-R-E-A-D, but too bad it's occupied. This can happen. And we allow it to happen. Okay. First of all, I want you to know we allow it to happen. If we have a collision, then we need to take care of it. So what is a hash collision? Hash collision means I may have some hash function. The hash function can be even more complicated. My hash function just now I introduced is a 2 simple one. But if even you have very complicated hash function, you may still have 2 different keys. For example, just now is bread and pizza, but they produce the same hash value. Then they will compete in a room. For example, just now, if I use your student number to put it into a room of hotel, maybe this student is 1, 2, 3, 4, 5, 6, 7. I take the last 3 digits, 5, 6, 7. The other student is 9, 9, 9, 9, 5, 6, 7. Also 5, 6, 7. Then these 2 students had to be collide into a room. And suppose we only can host 1 person in the room, then we cannot do it. And for example, if I want to hash mango, too bad, it also collide with the pizza. How do we choose? Can we go and try to choose a hash function that does not cause a collision? Okay, it's impossible, unavoidable. Okay, no matter how good you are, you can reduce the chance, but it's hard. It's actually going into the realm of math. Okay, and the pigeonhole principle says, because your universal key is larger than M, the size of your bucket, you will definitely have collision. Okay, for example, just now I want to map all English word, which is the size of your universal set is 2 to the power 140. And you want to map it into a smaller number like 1 million, you definitely have a collision. So how do we cope with this? Maybe we want to choose a better hash function, but as I said, it's hard to find. And if you do that, you may need to recopy the table. Okay, what I mean is, if collision happen, then I use another hash function and rehash everything, which is not that wise. Okay, and you will have another collision anyway. It doesn't solve the problem. We have 2 more ideas to help. One is called chaining. One is called open addressing. Okay, that means what if 2 items want to compete for the same slot in the hash table? Chaining is very simple. If 2 items hash to the same table, instead of storing one item in each of the slot, I use the linked list to store them. Okay, so just now, if I have coffee and mango and also bread, they will be in the same linked list on the slot number 5. Okay, and then the total space you need to be the size of the table plus the number of items, which is n you inserted. And the linked list size is n. The insertion is inserting any key. You actually calculate the hash value for the key, and you load up key and add it to the linked list. Searching is also the same. You use the hash function to look for the slot and search it in that linked list. What's the worst case? Worst case is everyone go to the same linked list. But if that happens, that means your hash function is very problematic. Your hash function is hashing everyone to the same slot, okay? Which can be ON. So remind me of this. Everyone pointing there. So every hash function pointing to the same single item, okay? If your hash function is something like that, it's a bad hash function. So actually, you have something called good hash function and something called bad hash function. And it's an art to study that. Let's be optimistic first, because I want to talk about some theoretical search. Let's assume something is called simple uniform hashing assumption. I assume there's a function that can map it evenly. Let's imagine that, okay? Imagine the world is so good and we have this hash function, and the key will be mapped independently, okay? It's almost random, but not random. It is deterministic. So it's a little bit probability. What is the expected number of items in the bucket if you have n items and n bucket? Very simple. I have n items and m queues. If the function can map you uniformly randomly on everyone, how long is each queue? You have n students, you're going to queue for food, but I will assign you randomly on the queue. How long is the queue? Very simple. If it's random, it's n over m. That means each linked list is n over m. Okay? And we have something interesting here. Usually, and then sorry, if it's n over m, that means the expected search time is 1 plus n over m. Right? 1 is the time you compute the hash values, n over m is the length of the linked list. And if you assume the hash table size is bigger than n, which usually we do, then we have constant time because n over m is less than 1. Okay, so that is the result. We can achieve O1. In fact, this linked list implementation is similar to the current hash map in Java and C++. Okay, we'll talk about that later. It's similar, but not totally. I think the Python one uses trees. Yes, wishful thinking. So if we can assume the uniform search time, the so-called expected search time will be O1. Of course, you can be really, really unlucky to be ON, but it's very unlikely. And the insertion is O1 because you just insert in the linked list. Reality fight that we actually do not have a simple uniform hashing. And also, your data is not cooperating. What does that mean? Our data are not random. Some data, your keys has a lot of patterns into it, hidden patterns. What does that mean? The keys in the pattern can affect your collisions. For example, let's say I want to hash. Very simple. My hash function is just take the first letter, like just now your midterm value assignment, right? Just take the first letter. Is it uniform? Is it you suppose every letter has the same number of words? No, right? Why? Most English words start with S or T. And you only have very few English words start with X or Z. If you look for dictionary, you know. So that means the hashing function is not uniform. How about we make it more complicated? We want to do this called sum string, okay? What does that mean? Every letter I convert it into a number. For example, A is 1, B is 2, C is 3. And for word, I add in the numbers. Do you think it's random enough? I try to random. For example, H is 8 plus 1 plus 20 because H is the 8th character, A is the first character, and T is the second character. It's bad because this is the distribution. If you go for all the English dictionary and you do this math for all the words, you have this distribution. Is it bad? You will see that a lot of words has the number around 100. Then that means your bucket at the 100 point, at the linked list is very long. So that means in conclusion is don't design for hash function, okay? It's very hard. Usually the hash function they did it in the nowadays the whatever package is undergoing through very long study and experiment. Yeah, unless you really want to do but of course, let's just be optimistic. And if you really want to do hash function, there are two very popular ones, okay? One is called division method, very simple. The hash function is the hash function modular the table size. Okay, this is a very simple hash function. For example, if my table size is 7, and hashing 17 will be 17 modular 7, which is equal to 3, and so on. This is very simple division method. Two keys will collide when their modular is the same, right? Now we go to math, and we talk about some movies. Anyone watch the movie called Mercury Rising? Very old one. Maybe even your parents didn't watch. No. Okay, that reveals your age. Mercury Rising is an exciting movie about this agent try to protect an autism boy because this autism boy can find prime number easily. And this autism boy become a national danger, and this agent needs to protect him. Why? Why prime number is a national security? Let's see. Go back to this. Two collision will happen like that. Collision is unlikely if the keys are random, but what if your table size and your key has a common divisor, common factor? That means they're both divided by something. For example, 15 and 12 are both divided by 3. You have a common divisor. Why is it so bad? Because if you have a common divisor, if K is the key divisible by D, that means if you assume M also divided by D, what does that mean? That means your hash values is also divisible by D. Did you get the math? Okay. If your key is divisible by D, your table size is also divisible by D, then your hash value will be divisible by D. What does it mean by your hash value divisible by D? That means your hash value is only going to be the multiple of D. Then your collision will be very big. That means if your table size has more factor, more divider, then your chances of collision will be bigger. So what is the number for the table size to be the best then? Prime numbers. That's why hash table size usually are prime numbers. Because if your hash table size is a prime number, you will reduce a lot of chance of collision. And that's why in the movie Mercury Rising, the hash table size, the prime number, is not only for the hash table size, but it's for password. Okay, we'll talk about the password thing in the next lecture. Okay, so that's why the moral of the story is, if your table size with this division method has a lot of divider or factors, then you will cause a lot of collision. Okay, the chances of utilization will be 1/t. And yeah, that's what I say. I try to choose a table size with prime numbers. And of course, the other drawback of the division method is actually division in computer is considered slow. We prefer multiplication. Multiplication is when you get a number, how do I map it into a small number? Let's assume we have a table size of m, and the m is r bit. Okay, m size is r bit. Okay, so 2 to the power r. And the hash key is w size. That means the hash key can be 2 to the power w. And I anyhow find a constant, a. And what I do is this. Wow, very bad formula. What does that mean? I have a, I throw in my pk there, and I compute this. Why do I want to do this? Let's analyze it step by one. Okay, first, if a and k are double bits, this term here, a times k will become 2 W bit words, right? Because a W bit words times a W bit words will become a number of 2 W bit words. By modular 2W, it means I only take the lower W bits. Modulo, I will truncate the higher bits. But what I need is, I need an R bit words. Why? Because my table size is 2 to the power R. I only need an R bit words. That's why I take this R bit. How do I take that R bit? By removing the W minus R bit at the end, which means I divided it by W minus R. In binary, shifting is equal to division. You shift W minus R bit, it means you remove the last W minus R bit from that. And finally, you get an R bit number, and that will be your table entry. And this is a lot faster than the division method. Okay. And because I don't know whether you noticed that multiplication is always faster than division. And if you get a is an odd number, you get a reasonable good hash function. Okay. And that is called talk about the collision training and hash function. We'll go to the last one, which is open addressing. I think it's a good time to take a little break. Okay. So relax your brain a bit. We'll come back for the open addressing. The open addressing is try to use the hash table without any linked list. I see the what? Sorry. Can you explain the multiplication method again? I'm confused. Yeah, usually people are confused with that. Make it simple. Make it simple. The multiplication is you take in the key k and just use this formula. Okay, and this formula will produce a number that is in 0 to n minus 1. Because you want to put it in the table 0 to n minus 1. And m is provided to be R bits. So this formula will change k that is W bit to an m that is R bit. So you can change think about that. So again, a times, because a is W bit, k is W bit, multiplication is 2 W bits. For example, if you have a 2-digit number, 99, multiply another 2-digit number, 16, the biggest number is 4-digit. Okay, if you have 5-digit number, multiply 5-digit numbers, the biggest number is 10-digit. Okay, so a W bit number multiply another W bit number, the biggest number is 2 W bits. And then we don't want a two double bit number because it's too big. So what I do is I modular 2W. When you modular 2W, it means I only want the least 2W bits. Okay, for example, let's say if you have a number 123, what does it mean by modular 100? Modular 100 means you take the last two digits, right, which is 23. So if you have a number with 123 and 45, what does it mean by modular 1000? It means I only take the last three digits, which is 345. Okay, so this one will truncate and modular that and make only the last W bits. And I still don't want W bits. I only want R bits. So I want to erase that by divided by shifting W minus R bits. Shifting means I will shift the bit to the right, and anything on the right side will be erased. So lastly, I will remain a number that's R bit. In the midst of it, it just go back to this is I try to change a number from K that is W bit to a number that is R bit. And this truncation somehow will give you a good way to mess around with your number and become a hash function. Okay, so that is about it. I don't want to clarify about the quiz questions first, okay? Let's leave that later, maybe after the lecture or something. Yeah. Explain the multiplication again. Talk about the implementation of ADT. Did you go for my ADT lecture? Implementation of ADT, of course, refer to the implementation. ADT is the specification. Implementation is the implementation, which is, for example, I can actually implement the key value search by a linked list. The specification, the usage is the same. So if you go back to this slide, if I want to implement this, I can don't use hash zero. I can don't use binary search tree. I can use a linked list. I can use an array. Just very slow. Okay, that is the implementation. But this one you're seeing here is called the interface. That means what my data structure can do. But I don't care how it does it. And this is called the ADT. Okay. And the rest are quiz question. I will actually leave it later, okay? The rest are quiz question. I will leave it. No. Okay. This one I always say so. Go back to my lecture. Please go back to my lecture because for the deletion of AVL tree, every node you delete, you may cause a rotation for all your parents. I already demonstrated in the class. Please go and see the lecture and the notes in the class, okay? This one, middle element in the list can still be the smallest or the largest for quicksort. Middle element means the middle position in the list. Doesn't mean it's the median of the list. The middle position can still be the largest or smallest. So after you pick the middle element, after partition, you will be one side have no entry, the other side have n-1 entries. And you can repeat that forever, and that's why it can still be n squared. Okay. Let's continue. Open addressing. Instead of putting all of them into the same bucket, I find another bucket. Look at this. I want to implement my hash table without the linked list. Why? Because I don't need to do linked list. Why linked list is bad? First, linked list is bad is because, yeah, it's very difficult to implement. Second, in a operating system or computer architecture points of view, linked list is fragmented memories. That means your memory can be anywhere in your memory space. To look for them is difficult. You need to rely on the OS and search for them. But if you put everything in a table without the linked list, then I know the neighbor. Okay, there's a good cache performance or whatever. So that's why I try to avoid linked lists. But then you have collision. How? If I hash another value, let's say hash of f is also equal to. Too bad the slot 2 already have A. How? That is what we try to solve it here. In open addressing, we will think of a way to settle F without adding a linked list. So if you have collision, I do something called probing. What is probing? Probing means after the collision, I see if the next position is empty. If the next position is empty, I put F there. Oh, too bad, it's still occupied. I see next position. Too bad, it's still occupied. I see the next position. Oh, good. Now I finally find an empty seat. Then I put F there. Is it okay? Will it work? Can I find back F? The problem is, can I look? If I try to see if F is in my table, can I find it back? So to insert the key, what I do here is, if the collision occurs, that means my original position is occupied, I put it in the next position. I put it in the slot I plus 1. I want you to think about this in this way. Originally, let's try to find the position hash value of F. If it collide, you have one collision. Okay, remember that you have one collision. I search for HF plus 1. If it's not colliding, I put it there. But if it still collide, I put it in HF plus 2 position. If still collide, I put it in so on. So what is the red number means? The red numbers is actually the number of collision. Okay, I put the numbers in the slot of the hash value HF plus I, such that I is number of collision. And actually, I can play more about it. I can put a function there. The next position I search is actually Fi instead of I. What does that mean? After I collision, I put the value Fi of that. For example, this original one, I call it linear probing. Why is it linear? Because I is 1, 2, 3, 4, 5. That's linear, right? I can do quadratic probing. That means the next position, instead of going to HF plus 1, HF plus 2, HF plus 3, I don't do that. I do the first collision is this one, right? The next one I will go to HF plus 1 square. Oh, the same lah. So I check for 3, right? Too bad, it collides. What is the next position? In the last linear probing, I will look for the position 4 because it's HF plus 2. But in this quadratic probing, we do HF plus 2 square instead. So I jump to this one to see if there's any space. Okay? Instead of looking for one seat and one seat temporary and so on. So I put F there. So this is called quadratic probing. In a way, you can actually modify the function F anything you want to make the probing more interesting. So let's redefine the hashing function to be hash key with I such that I is the collision. So the hash function of linear probing is simply the key that hash plus the number of collision. Quadratic probing is the hash value plus the quadratic number of collision. And you can do some other very complicated thing. I can even make the function even more complicated. I times another hash function. Okay. So, but how do we get it back? Now I hash f into the function. The f is actually after some collision. Okay. I don't know if f is in my table now because I don't know. I want to search it. That's the purpose for searching. I don't know whether f is in my table or not. So when I search the table now, I hash the value of f, which is 2. But now I go to the slot of 2, A is not f. Do I stop? F is not in the table. Too bad. No. In the probing or in the open addressing method, you look for the next one. So if the bucket is the key, it's good. If the bucket is equal to null, then you not find. Otherwise, you increase the counter. So after F, you look for 3 and 4 and 5 until two possibilities. One is you find the item F. One is if you met a null. Okay, that is for searching. So for open addressing, one of the not so good thing is when you find the slot that does not have your items, you cannot stop. You have to continue searching in the table until you met an F or null. Okay, this is the algorithm. So do we search? We first start by the bucket that is the key and the number of collision, and afterwards you go to the next position. So for this hash function, it can use for linear probing or quadratic probing. It's the same manner. So now our method works for insertion and searching. How about deletion? Deletion is you search it first, right? You search it first, and then I set a sort to null. Let's say I want to delete D now. What is the problem now? If I delete D, will there be a problem? What would be the problem? If I delete D now, I lost F. Why? Because F had to be start searching from the slot 2 and go all the way until you meet a null or F. But now you delete D, so when I go to the slot 4, is a null. That means F is not here. Too bad. Then what do we do? In open addressing, we need to differentiate slot to be deleted or empty. So in open addressing, if you want to delete a node, you will not change the node to be empty. You will change the node to be deleted. So go back to the searching. We start to search for F in the slot 2. We go to 3. 3 is not F, too bad. You go to slot 4. No one's there, but you don't stop because the slot is not empty. Someone was there. And it was a chance that F can be bumped into another room because someone was there. So in the searching, if you meet an empty slot, you stop. If you meet F, you stop. But if you meet a deleted slot, too bad, please continue. Okay. So how about now, after this, if you want to insert something, yes, you can reuse the deleted slot. For example, now I want to insert something with the hash value 3. I will go to 3. Oh, too bad, C is there. I move to the next slot. Oh, next slot is deleted. So I can insert my stuff there. Okay. So we can reuse a deleted slot if it's deleted. So let's have a deleted example. Let's assume hash F is 2. So I insert F is slot 5. When I delete D, so slot 4 is so-called empty now. If I search for F, I will start from 2. I will search for 2 is occupied, but it's not F. I go to the next slot. Is F there? No. If F here, but it's empty what? Empty, okay, because it's deleted. I will go to search F. Oh, bingo, I find F. That's how I search for F. How about I insert another new key there? I want to insert Z. Z is going to be inserted in the slot 3. But now slot 3 is occupied by C. And I go to the next slot. It's 4. Oh, 4 is good because I can insert Z there. Why? 4 is deleted. Now I insert Z and so on. Okay. So that's how we actually manipulate our hash table. And don't worry, this one we will repeat it in our tutorial. We have some exercise for you to do. So in the tutorial, we'll go through this again. Some property. First of all, hash key must be able to reach all slots. For every bucket, you can be able to reach all slots. Why? For linear protein, you can do that because the increment of I can reach all slots. But for example, one thing you could go back and try, and just actually in one of the midterm answer. What if I use quadratic probing and my table size is 10 or 100? You will find that some slot cannot be reached. For example, if the table size is 10, do you notice that all square number ending with only a certain numbers? All the square numbers. The last digit is only 1, 4, 9, or something. You won't reach. There's no square number ends with I don't know, ends with 2, something like that. Okay, you go and figure out that. So if your slot is 10 slot, you modular 10, but square or quadratic probing may not be able to reach some slot. And you want to be uniform hashing. Every key is going to be likely probability, and this is hard to design. Okay. And usually what people do is they either have very good math, probability and statistics, and they may need to something called empirical proof. What's empirical proof is I try to simulate my hash function and I do a statistic to see how my hash function do and do experiment. Lastly, what is the performance now? Under uniform hashing assumption, what is the expected number of time for insertion, or the expected time for probing after we insert M item into a table size M? Expected time, not expected time for insertion. What? Let's see. You have to make a decision now. Huh? Who says A? Who says B? Who says C? Who says D? Who says E? No one says E. You say E? Why is it E? Oh, you are not. The answer is, if your table size is M, how do you insert the next item if you're already insert M item there? You cannot. If this lecture have 200 seats, you already have 200 students here. How do you get one more student seat here? You sit on the floor. Okay, you cannot. So it is a question. Actually, next time we'll talk about what if we insert items in the table when the table size is full, which is the next question. Okay. So for chaining, it's okay. Chain, because the question is actually if it's chaining, N is equal to M. So the performance is still constant time. Each chain is that. But for open addressing, when the table is full, you cannot insert anything. Okay. So let's see. For whatever reason, let's do open addressing. This is where the math got you. Okay. I will call something called the load. The load is alpha. That means how much percentage the table is already occupied. The percentage, very easy, is N over M. So the claim is, if you use open addressing, the number of probe is equal to 1/1 minus alpha. Okay. So why is that so? Math law. Okay. But if you want to use the formula, let's don't go for the proof first. If you want to use the formula, for example, if your tables is 90% full, then your number of probe is 10. But what is the good news? The good news is it does not depend on n. That means it does not depend on how many numbers. That means if your table size and n, let's say you have 1 million people, is 10 probes. You have 1,000 trillion people, is still 10 probes. As far as your occupation rate is 90% of the table. So that achieves the constant time again. But why is the proof? Too bad. Let's have some probability. What is the probability of the first collision? First collision is n over m now, because it's the choice, right? You have n items there. The chance of hitting one of the item is n over m. After first collision, the chances of next collision is, because you left n over n minus 1 items and m minus 1 thought, the next item's chance is n minus 1, n minus 1. The next collision is n minus 2, n minus 2. So the math goes like that. The number of probe is the first probe plus the chances of next probe. The chances of next probe happen is you need to have this probability of n over m, right? There's a collision. And there's expected number of probes afterwards. The expected number of probes afterwards is n of n minus 1, n minus 1, and so on. And you have this formula. And this one, you notice that every n minus something is less than n over m, and is less than alpha. So you can convert this into this one. And finally, it becomes 1 plus alpha squared plus alpha cubed, and so on. And we notice that alpha is less than 1. And if you know that it's arithmetic series, this is less than 1 over 1 minus alpha. That goes a proof. Okay. So the important point is how to keep your number of items inserted under a certain load. So next lecture, that means probably next Wednesday, we'll talk about what if your table is full. Let's say my table have 1,000 empty slots. And now if my table is very full, let's say filling 900, what should I do? Should I resize the table or what? So next time we'll talk about that. Okay. For open addressing, the advantage is you save space. You don't need to use linked list. You don't need to reallocate memory unless you're doing the resizing we talk about next week. And also, good thing is better caching at performance. What do you mean? If I want to look for every memory entry, if the memory is everywhere, I need to, from the CPU, go to the RAM, get the memory, go to the RAM, get the memory. But think about that, if it's probing, I look for the trunk of memory, let's say the nearby 10 slot. I can put the 10 slot in my cache. Then I can look it up in my cache for the next 10 collisions without going to the RAM again. So the caching performance is a lot better than other memory model. Okay. Of course, the open addressing have this problem. The data will cluster. You are the clustering means after the probing, your hashing values, the items will be very concentrated on certain parts, and that is highly related to the hashing function, and especially serious with linear probing. Okay, and also it's sensitive to load. If your load is close to 1, that means your table is almost full. You got this. This is the graph of 1 over 1 minus alpha. You can see actually things are very okay before 80%. But after 90%, the table the number go crazy. Okay. And that's all for today for the problem. Okay. So next time we'll talk about what happened if your lows go here. What do we do with the table to make it better and so on? And any questions? Oh, no more questions. But if you have more questions, please let me know. And remember, very importantly, read this carefully. For those latecomer, remember to bring pencils. Remember to bring pencil. Bring pencils, okay? Very important. Say 3 times. Bring pencil. Tell your friend, bring pencil, okay? Tell your friends now, bring pencil. I love you, okay? Bring pencils. I love you. Bring eraser. I even love you more, okay? Bring pencils and eraser. Thank you.